All right, everyone. Thanks for all of you for coming today. I have a really amazing guest, Dave Airlie, the Red Hat Distinguished Engineer, and he's going to talk about why compute needs commoditization. So I'm going to get out of the way, Dave, and let you take the floor.
Thanks, Ray. Yeah, so this is kind of like a follow-up to a talk I gave a few years back about CUDA and open source. I've done a couple of them over the years. So to start, this is pretty much going to be opinionated. It's probably also going to be, this is not Red Hat's opinion, this is only my opinion. And it doesn't reflect any of the work we'll do in the future or any of our partners or anything like that, because we love everyone. But yeah, this is just me having a rant mostly about the state of what compute is now, and really, what we could do to possibly change it, or what we can do to, make it better. But so, yeah, the title is Why Compute Needs Commoditization. So I'll start off with the question: what is commoditization? What do I mean by that? The first word that usually gets thrown around is heterogeneity. That word always means we reach for a dictionary. So I'll try to go beyond what heterogeneity means, more into, well, you want compute to be easily available. You want it to just work. You want everyone to have access to it. You want it to be, no matter what device you plug in, it should just switch on and accelerate and do. And if they've got apps running, they should just be able to use that features of that device if they're there. You shouldn't have to go and reach out for special, drivers or reach out for special stacks. It should just all be there in your operating system. Everyone gets it. It's like you install Linux from some distro and you have whatever devices you have, and it just works. And we have some good examples of that in our current, most devices just work. Like you don't expect to be installing vendor specific stacks for hard disks. You don't expect to be installing vendor specific stacks for your keyboards and mice. You might have there might be enhancements and things, but the baseline should be common across all devices. And in Linux, we've had that across, like the Linux kernel is pretty much the great example. Like all the vendors will put stuff into that kernel, and the kernel then will be, as an easily available and just works out of the box. You could go beyond the Linux kernel, so we've got compilers, GCC. It's just like in the old days when you install Solaris, the first thing you do is I have no compiler. Oh, I have to get some compiler. Oh, I got to pay them, or I can get GCC. Now at Linux, it's like the compiler is just going to be there. It's easily available. It just works. It might not be the most optimal compiler in the world. It might not be like the greatest compiler for doing certain x86, things, but we could. Often there's like Intel had produced Intel compiler for years. There's been AMD compilers. A lot of them have moved to using C-lang based compilers, but there's always been a kind of a baseline platform and easily available just works baseline, and sort of enhancements that are vendor specific. And again, we see that a little bit with graphics stacks. So graphics, we've got like Vulkan drivers in the out-of-the-box distros, but we also have some vendors who supply their own Vulkan drivers separately in their own stack. We have, OpenGL has become pretty heterogeneous. So most of these things, they just work, and that's sort of what we want to aim for compute. But right now with compute, this is not in any way true. So that's what I wanted to sort of aim for. So I'll just a quick run of, what is there out there at the moment? What do I mean by compute, I suppose? If you look at from the vendor positions, where we've got but there's nothing that works really out of the box at this stage. There's CUDA, which is like the leader in the space, runs on everything NVIDIA makes, and does a pretty good job at the part of the commoditization that it runs on at least everything the vendor makes. So if you've got an NVIDIA device and you want to learn CUDA will just work. And then you've got, but CUDA is completely proprietary, totally closed source, no interest, and you can't really fault them in any way. They've made a huge market. They've got a massive moat. They know it. There's nothing you can't really go in and demand that they open source this thing or anything. It's like they've made a lot of money. It's making them their hardware sales, so can't really fault them on it. But doesn't really get to what we want, is what's commoditized. So like a lot of vendors then would look at CUDA and went, well, maybe we could reproduce the exact same thing. They don't really get the whole second mover thing, maybe, but it's like, oh, well, we do open source and it'll be fine. So then we got ROCm from AMD, which is like, okay, we kind of got the open source piece of it, but we don't really have anything like heterogeneity. Like it doesn't even run on everything AMD produces. And if you can get it to run on some of the stuff AMD produces, you could be quite lucky. I've seen recent things with George Hotz complaining about how bad it is, and he's actually trying to build systems with it. So yeah, it's got open source. You can look inside it and see how it runs, but again, it is very AMD specific. It lacks a lot of features that you would want from a heterogeneous stack. The next sort of step down that road then is the Intel oneAPI. They've gone a bit further. It's an improvement on the AMD situation with ROCm, and it's like a definite improvement on the CUDA situation. But it's not really open source developed. It's probably open source released. You can join in ways. There are some community input to it, but the stack is still very Intel specific, and it's kind of it's still being run. I'll get into this a bit later. It's like it's a product for Intel, and that's what they want to do it. But again, from a point of view of wanting to have a heterogeneous stack, if we could make oneAPI run on everything, it could be the thing. But again, because the market's so defined with CUDA, it's really hard to know which horse you want to be backing. But if we step outside the big CPU vendors, there's also a bunch of other type of accelerators out there. I've just given examples here, but there's lots of, I think there's not lots, but there's a few other ones. You'll see things like the inference accelerators. These are like just matrix multipliers. You see them on the IMX 8M, I think is a plus, maybe there's a Vivante one. It's pretty much based on their kind of Etnaviv thing. You can see there's an open source developer working on reverse engineering and implementing a stack, Tomo. So that's it'd be an interesting target, because they're a lot more of a narrow target. So the targets for CUDA, ROCm, oneAPI are generally GPUs, possibly FPGAs. I haven't seen much scope for them being used on FPGAs. Like the idea is there, but I think we have to see if that's going to play out. But these inference accelerators are way more targeted devices. Like they can only do a very restricted set of operations on and you generally end up pairing them with a general purpose GPU and having them just offload certain things through the inference accelerators. And then you have the other end of the market, which is the big end of town, where you have training accelerators. And these are devices that, like, you put 8 of these cards into a server, and all of them are used by one application to just do training as fast as possible. And you schedule them so that something is always using all 8 cards. You never really have a case where you're splitting up the cards or trying to sub-allocate the cards. So I think the best example of that is probably the Habana Labs Gaudis that are out there. I think you can even get them out of AWS at this stage. But that's kind of where I see the vendor compute stacks. I said there is some FPGA work that I think people are interested in, but I haven't seen much traction in oneAPI or ROCm in that area. I think oneAPI has probably got more FPGA concepts in it. But that's sort of what the vendors are at the moment. But in terms of the open standards and open development in that area, it's kind of a bit more lacking, I suppose. So we've had OpenCL. I expect a lot of people are kind of familiar with OpenCL. It's been around quite a while. Apple were the initiators, gave it into Kronos. Let's just say it hasn't been a stellar winner at anything, which is unfortunate. I think it's possibly just not had the investment from enough of the companies. I think NVIDIA going down the CUDA route and pulling out of, like, really stopping work on OpenCL kind of killed it in a lot of ways at the time, which was unfortunate. But unfortunately, it is the only real open standard in this area for having like a runtime compute thing. That it can run on all the different vendor stacks. You can get the OpenCL to go on NVIDIA hardware, on AMD hardware, on Intel hardware. It can be useful in the restricted hardware case. For some of the work, you still need separate API for some of the other pieces. And yeah, maybe with Carol's Rustical work and with other work for vendors, we can get some sort of OpenCL traction. It would be great to see it kick off again and going, but not hopeful. But who knows? I think a lot of people got burned by it. I think the problem with the quality of a lot of the OpenCL stacks that were released was, kind of made people like weary of it. And we've had that problem with OpenGL in the past, where vendor OpenGL stacks are subpar, and we got around a lot of that by open sourcing them or using Mesa as a baseline, and possibly doing something like that. GCC level, like this works. It's there. It's in the box. You can use it. We've tested it on the main vendors. That's great. That's a lot for people because they can trust that it's going to work. And we've done that with OpenGL, and we've done that with Vulkan. So maybe we can resurrect the OpenCL in that way. Sickle again is an open standard that's kind of a bit higher level than this. It's more like the C++ programming interfaces for parallel compute stuff. I've see Ronan's he's more Sickle contributor than I have done some Sickle contributions a couple of years back. It's interesting from my interest in Sickle at least comes from more the environment around Sickle. The fact that it's got the C++ API to it, that's a header-based API, isn't my favorite thing. But I sort of think of it as being the rest of the ecosystem it requires you to build is valuable. So having things like the Sickle, like a runtime. So if you have a standard runtime that Sickle targets, like if it's OpenCL or if it's just a higher level one that then goes out to OpenCL or Vulkan or level 0, the oneAPI runtime, you have to build that infrastructure. You got to build infrastructure in LLVM. You got to build infrastructure in Clang. I'd like to sort of, this is where Sickle wants to go, but what I'd like to see it enabling is other languages to get these features. So having, that the Rust developers can add parallel APIs, and suddenly they can use all of the infrastructure that we've built for Sickle and validated using Sickle. And, people can use Sickle then in the background for their Pythons, stuff with target Sickle. And we could, again, other areas I see it being useful is probably something more like, we would use it in PyTorch as the sort of abstraction for C++. That would be, I'd like to see it start going. I think there'll also be C++ standardization around the parallel programming stuff, and interesting to see if that can help drive things, especially when we start getting into how does GCC implement these extensions. How is that going to work? And then there's the kind of a bit of an outlier in that Vulkan Compute is out there. It's not ideal for doing compute stuff, but it is at least ubiquitous in that it just works. Everyone gets it on their desktop. It just comes with nearly every distro, and it seems to pretty much work across vendors. There's been some concepts of adding more features to Vulkan Compute to try and bridge that gap with OpenCL, and I think that could be very interesting to try and go down that road. Things like SVM, adding features like that could, might just get it across the line. It doesn't have the concept really of like library sort of functions where you've got optimized special paths, which a lot of things really would like. But yeah, there may be a possibility to try and bridge that sort of gap. Again, it's going to be hard to see. And I've realized one thing I've kind of left off this thing is slide with SpearV is for you who don't know, SpearV is like a intermediate representation used for both OpenCL and for Vulkan. There's two different implementations, or not implementation, two different sort of extensions to the specification, depending whether you're doing Vulkan or OpenCL. So that it has flavors, and they are not directly compatible. You can't feed OpenCL's SpearV to Vulkan, and you can't feed Vulkan SpearV to OpenCL. But it gives you, I suppose, it gives you a layer between your runtime and your build time. and I think this is where I also one of the areas I think Cycle falls down, is that because it's only abstracted up at the build time. Currently, if you have 3 or 4 Cycle implementations and you want to build your application, you have to pretty much target one of them. Now, I think the HIP Cycle project is trying to move towards something better, but yeah, the current sort of way it's designed is it's build time independence. It's not runtime independence. And again, for the works everywhere, just happens to be great. That needs runtime independence. I need to be able to build binaries and just have them run. Might not be optimally running, and then maybe we can rebuild them and get more performance. But I want to be able to put something in a distro and have someone run it 5 years later on a new graphic card, and it still should run. Now, it might not excel, it might be slow, but it should at least run, and let the user figure out what needs to be done. And that's a big area we're missing. You need that backwards compatibility if you want to make this commoditized and available to everyone. Why I think SPIR-V is important is it lets you do that. You have an abstraction layer there. It's where ROCm, I feel, falls down in a large way. ROCm, again, pushes that abstraction up to the build. It's your source code builds all the way down to assembly. You can't just build it to the SPIR-V and then use that SPIR-V later. And I think that's a big fault in the ROCm stack. The Intel oneAPI stack uses SPIR-V as its intermediate representation, and that's a good thing. And it has some little workarounds to put inline assembly and stuff through it. But I think it's a good design from that point of view. Both level 0 and the OpenCL can consume SPIR-V. Even NVIDIA have an abstraction at that level. They use PTX. They don't use SPIR-V, but they have their PTX layer. So I feel that's one place AMD made a decision that it bites you, because you can never get an old binary to run on a new card unless you've rebuilt it, and that's great for some scenarios, but not for every scenario. So I want to just take it to the level of, from a distribution vendor's point of view. Again, I'm probably talking more Fedora than RHEL, but just from somebody who builds distros quite regularly. The big, of course, open source is the first sort of challenge. We're not going to put something in a distro unless it's open source. It kind of rules out CUDA. It makes it really hard to put things into distros if you don't have the rights to redistribute them and change them and rebuild them. There are people trying to, that will package these things, but they're never as integrated as you'd like, and you can't rely on them being there. One of the big problems I find dealing with vendors in this area is and again, this may be something we haven't, just doesn't get explained, or they don't really care, is, people hear, we just need to open source it. And for some reason, most vendors go, just do what Android did. We'll throw it over the wall when we're finished it. And you're like, okay, no, we want to open source development. And it's like, what's the difference? And it's like, you develop it outside the company. You develop it where other people can join in, other people can, with, and should be able to join in your process as if they're working in your company. So you shouldn't be having that many internal meetings. You shouldn't be having hidden away, agenda. You shouldn't be having plans. But these things don't always, we get that doesn't happen. But so this is where, if you go down the list, CUDA is totally out, doesn't open source. ROCm is open source, but it's the throw it over model. There's no, if you open a bug on the ROCm, anywhere in the ROCm things, it's very unlikely any AMD engineer will ever see it. Or they may see it, but they won't ever get time to fix it, because you're not a customer. There's no path of revenue. There's no reason for their program manager or their project managers to pick up this stuff. So, and that may change, but currently that's just the feeling I have. And oneAPI is kind of in the same area. It's like, it's better than ROCm. There's more talk outside. There's more bit of community trying to be built. There's a bit more effort. But it's still very focused on Intel's timelines. And that, I get that this is where I sort of get pragmatic of these things. It's like I'm ranting a bit, because I understand companies have missions and companies have to sell stuff. But in terms of from the pure distribution and open source point of view, we have this thing in Red Hat we call the project versus product distinction, which a lot of companies need to, I'm not saying they need to adopt it, but this is the distinction that you have to get into your mindset to be successful doing open source, is that your company has a product. Your product can be downstream of an open source project, but the product should not drive the up source. You should have your engineers working on the upstream project, and then have that group can then consume that and then package it up and then produce your product. And then your product, you stick your own name on. So you know, in Red Hat, we've got kind of like, it's harder with Fedora RHEL because that's a big gap, but CentOS Stream and RHEL. It's like we have a CentOS Stream project and we have the RHEL product. The same sort of stuff goes into both of them. We just make slightly different decisions at the end internally for what we want in our product versus what's in the project. But again, so CUDA, nothing, they're just product. ROCm, so product, it's driven by products. Release schedules are pretty much product aligned. There's no real project. You can't have some, you couldn't, I suppose the best way of doing it is if I wanted to fork ROCm, or not fork it, but if I wanted to work in the ROCm project and produce something that was, a different product from it, could I do that? How hard would it be for me to do that? My expectation is I would have to fork the whole project to get anywhere. That there wouldn't be enough interest on the AMD side in maintaining my work or helping me get a way to maintain it. And I think oneAPI is in the sort of same area now due to product schedules and stuff that needs to drive it. I understand to invest in these things, you need to make money. But ideally, like setting it up as a project first with a different name. If oneAPI is your product, set up an upstream project with a completely different name that's, people can get around and actually invest in as a community as opposed to investing in his product. And if somebody like wants to produce something like a oneAPI like distribution for their device, well, they don't call it oneAPI because Intel has all the trademarks and stuff, but they could have, API 55 or something, and that's their version. But it's the same source code and everything goes back into the same upstream. Pretty much how Linux works. Like my thing is like, I believe the vendors have been dragged kicking and screaming into Linux. Like they had to be forced to make Linux the thing it is because of the licensing. But ideally in their minds, all of them would just consume Linux, add the one thing they want to it, but never give that bit back. But because of licensing, we've managed to get them to, we have to give that bit back and we have to make it maintainable. So I think, trying to build the Linux of the compute space is pretty much what, where we want to see it. Having something that all the vendors could contribute to. Again, vendors don't see it like that. They love control, and I get why they love control. But they've managed to lose it with Linux. Whether they can manage to lose it with these would be nice to know. But and the way I kind of metric this, the way I kind of go, can this happen is, and this is partly where the talk I did a few years ago is from. It's like, could you as a distro ship PyTorch or TensorFlow and actually have them work out of the box? After you install your distro on 3 vendors cards, like on the main vendors cards, Intel, AMD, NVIDIA cards, and maybe some of the ARM vendors, like Apple M1, some of the Molly's. Could you do that? And the answer is still like it's no for lots of reasons. Like you could build a PyTorch that just has a CPU accelerator, but what's the point? You then have to rebuild it anyway. Like the way we seem to have solved a lot of these is, hey, we just containered everything and we just everyone puts a separate PyTorch into a separate container. So you've got your NVIDIA PyTorch and your AMD PyTorch and your Intel PyTorch. And I'm like, yeah, that kind of sucks. It's like you want to be able to run, like, if I have 2 graphics cards and I plug both of them in, it'd be nice if they just both worked and both were used for accelerating whatever application I'm running and make everything faster. Like PyTorch is probably easier target than TensorFlow. TensorFlow has a lot of Google built into it. It's got the Bazel build system, which, I know there's a couple of people from Google on this call who probably either love the Bazel build system or really, really hate it. But I've tried to build TensorFlow a few times. It's tricky. But the other problem we face in the PyTorch TensorFlow space is CUDA kind of won by default. So when you're building, you've got your PyTorch, you've got your TensorFlow, and you've only got one backend to target, that's CUDA. Well, you're not going to really build the abstractions necessary to make that abstractable. You're just going to put CUDA where you need to put CUDA. You're going to get to the end, the goal you want. You're going to get it running. You're going to get it accelerated. Then stack number 2 comes along, and it's like, okay, we'd like to use SYCL instead of CUDA for some of these. Oh, yeah, we got to abstract this now. Now you got to pull all the CUDA stuff out to separate back end? How do we, so there's a lot of work done on the second person to get in there because the first vendor has that first mover advantage. So, could a distro ship these things? Quite unlikely at the moment. Even say, so the next thing is the GPU stack. So each of these open source stacks. So say I have ROCm, I have oneAPI, I have some other ARM ones, and they're all open source. Well, let's say just throw them in the distro. Why can't Fedora just have all of these things in it? Why can't we just take the vendor aligned product stacks and just put them in our distros? This is what everyone has been pushing for a few years. I go to a lot of meetings with people that like, well, why can't you just ship ROCm or I'm like, right, technically we can, but it causes a lot of other sort of unforeseen problems, and it causes a lot of maintenance and expense problems. So, we have pretty much a sort of an upstream first policy in Fedora. We would rather people move their products or their projects into the upstream if they can. So something like, if you look at all of these stacks, everyone's got a fork of LLVM, everyone's got a fork of Clang. Some of them have 2 forks of LLVM, some of them might have 2 or 3 forks of Clang. There's a lot of duplication of code in a lot of places. There's not much, like AMD are probably the best at pushing stuff back up to LLVM. I'd like to encourage Intel to push more of their SYCL backup stuff up to upstream. They've got their own compiler that's kind of an LLVM attached thing, but it's not quite the Intel graphics compiler. And one thing that it's hard for everyone to admit, but LLVM is a really bad compiler for GPUs. Probably has a bad plan. But yeah, there's way too many LLVMs out there in Clangs. And when you're a distro, and you find out that suddenly your distro has 6 versions of LLVM and suddenly pulls a CV out of somewhere, and you're like, oh, how do we do this? It causes a lot of problems. Also, even if you do manage to get everyone sort of base on an LLVM, then all of their attached, extra features that they've added on the sides, you end up in this nightmare of, well, AMD have moved to LLVM 17, but Intel hasn't moved yet, and they won't move for 2 months. But we need to move the distro forward to LLVM 17 because that's the way we work. So you end up having to do either a lot of compat packages, but compat packages with LLVM is a nightmare because if you load 2 LLVMs into the same address space, things get very, very funky very quickly. It's never fun for anyone. Even beyond that, there's the problem of, say, with PyTorch or TensorFlow. I want to do a PyTorch update today. Oh, there's a bug in the AMD stack specific to one place, but it works on Intel. But it need to update this one part over here first. There's a document in the Linux kernel called Stable ABI Nonsense, which is about the fact that, at least for the kernel with modules, it's really hard. You can get stuck in these places where you can't make any forward progress because if one module doesn't use your new API and when one does, you're trapped in this place where you can't use your 2 modules together, and then you can't move the kernel forward, and eventually it all collapses. It may be a bit hyperbolic, but it could happen. Doing this thing where you end up with a PyTorch that targets 3 different backends, or 4 or 5, scale it up as you get more ARM chips in there. How? Like you can't move your PyTorch forward easily unless every vendor has product alignment. Every product will have its own. Every vendor will have their own product schedule that will not align with distro schedules. And you could be halfway through an Intel oneAPI update. You could be at the end of a ROCm cycle. It turns into a nightmare. But I suppose one of the things is how do we move that forward? It's like, do we need to have a commoditized stack here? We need something that we can target at a base level. Everyone can use it. So why do we end up here? Like, why has this happened in this? I'm going to say it's vendor missteps. I'm calling some vendors out a little bit, but it's not really missteps. It's like vendor decisions made for practical vendor reasons or for internal reasons, but the community has gotten smashed about them. Well, for a start, a lot of the push in this space has come from like a HPC and a data center focus, which, that's where the money is. If you want to sell 20, 30, 40,000 GPUs to one customer, you stick it in a data center, a HPC cluster. But unfortunately, that is, that focus for the company has led to like products being very focused on that area with not much scope for caring about other areas. Like, it's like, well, we could have one person actually work on some sort of desktop level. No, we're not making right money on that now. We need to make, surprisingly, I think NVIDIA get this the best. They have since as far as I know, day one, that made sure that CUDA works for developers on their machines. It can be a mess to get installed, but it works for developers. Like my wife does machine learning work out here, and I just put Ubuntu CUDA on her machine, and she doesn't annoy me about it, and it works. I'm like, great. That's it's not even a great graphics card. They've done that work to make it at least work across their hardware base. They care about it on the crappy cards. They care about it on the good. They care about it in the data center because they understand that developers need to learn, and developers need access to the software that's going to run in production on the data center, but they need it on their laptop or in a small cloud. They don't want to be spinning up a cloud that's going to cost them like $100 an hour. It's like they want to be able to just do stuff locally and in their control. Again, I think that's where NVIDIA have done the best. I think AMD have totally dropped the ball on this. They're very focused on the higher end stuff. I've yet to decide on oneAPI. I think Intel have done okay, but again, it's the stack's such a mess to build or install. It's like, there's a lot of work to be done there. Again, the other thing that causes a lot of this problem in companies is a lot of these companies, especially I don't think NVIDIA really have this as much, but at least AMD and Intel are very client or server. Like they have two markets they care about. They're like, we're either selling to put these in laptops or we're selling to put these in servers. And the guys deciding stuff for the servers go, well, we want the graphics cards that can do all these compute things. And the guys in the client are going, we want the graphics cards to do all these gaming things. And we don't really care about the other things. And then, you'll find like, so oneAPI is so targeted at the data center mine and all that's great, but it doesn't really work when you want to stick it on your laptop because the people that, whose job it is to do that, it's like, okay, well, we're getting the money from the data center. We don't care that much. But I think there's one area I think that at least NVIDIA had thought this through a lot more, and it would be nice to see the vendors try and get that, bring it back together and just go make this work across all your hardware, and make it work across get all the other vendors' hardware, or try and contract other companies to make it work with your vendors' hardware. I should have added a last slide, but I forgot. Is that that's the kind of overview of where I think things are at and what's the non-doom and gloom, like what can we do to, this is very opinionated opinion, to make this work. How could we commoditize this? I think we need there needs to be more community development, I think, is what we need to get done. It needs to happen upstream, away from the vendors. The vendors can participate, but the vendors should not be driving this on product schedules and driving this on, shipping needs to ship tomorrow type things. There's a lot of work inside groups like the Kronos group, but again, this works very hidden away. It's very hard to engage a community around something that only the vendors can join. Like Red Hat weren't members of Kronos for years, and we only joined just before Vulkan started. And there was no real Linux representation from outside of the vendor community, which again made a lot of mistakes got made because of that lack of representation of distributions and how things are actually shipped to customers. That where I kind of see we try to. There isn't really a good forum for this. My kind of view on where we're going to go is I think Carol's Rustical work is a great start in the direction of at least getting a baseline. I think our recent sort of work with NVIDIA giving us access to their hardware through their new GSP firmware, that we could finally at least get an operating system driver that could in theory compete with their vendor proprietary stack, even if it requires using a huge firmware to do so. But it at least breaks that boundary that we currently could never ship an open source stack on NVIDIA because without the power management ability to scale up the clocks, things just suck. So that was all sort of limiting our ability to commoditize in the open source space, because the one vendor that everyone has hardware, we could never actually use in any useful way. There was never an ability to do a GCC level thing because it was always going to suck horribly on that hardware. So hopefully we can move forward with that. I kind of see it. I'd like to see the SYCL infrastructure sort of move into upstream LLVM so that other languages have it there, that they don't have to rebuild that. I don't want to see Rust reinventing all of the LLVM bits and the internals of any bits of Clang or whatever, the front end that they use. So I think that would be great to see, that if we start moving more of the sort of runtime stuff into the upstream. I go back and forth on this point. I do wonder sometimes if you look at the way gaming has kind of gone now with Valve's big push for Steam Deck and stuff in recent years, is like we've kind of come to the point where the standard for programming games API is the Windows API, and then we just emulate it. And now people are like, oh, that's horrible, because we used to have native games. But when you actually look at a lot of the native games, at least the native AAA ports, they were generally a Windows to Linux stack stuck in there that was closed source. So now it's kind of, well, we now have an open source Windows to Linux stack. Is that better? Is it worse? It's hard to know. But I kind of go, oh, maybe we just give in and say CUDA is the de facto standard for compute, and we suck at derailing that, and we just build a CUDA compatible runtime and make it work on all the different vendors. And it might not be, PTX might not be optimal, but you make your runtime be able to consume SYCL. You try to build out from there. Again, I don't know. I don't have 10 developers sitting around just waiting for me to tell them what to do here. But yeah, I kind of foresee like something with Mesa as a base, using the Mesa drivers, using the compilers that are in Mesa. We have GPU-based compilers for all the major vendors in Mesa. So using that, stuff we've built up from graphics and trying to push it out into compute. But there's a lot of work, and again, because the vendors are so focused on the data centers and their stacks, it's very hard to get the vendors to give you the resourcing. Or you go to Intel's Mesa team and you're like, oh, we'd like you to do some, could you interest in this? Like, oh, that's not our wheelhouse. We're just games and graphics. We don't do compute because we're siloed, and it's like that's the way it works. But try to break through those and get people engaged and see if we can build a bit more community around it and see, go with that. But yeah, that's kind of the guts of my presentation. So I can open up for questions, I think, if you want to. I just turned off the presenter. So if anyone has any questions, or I haven't read the chat. So.
Yeah. First of all, thanks. That's good. So I can say, so I'm independent right now. I have a relationship with Intel where they send me hardware and so on, so that I can complain to them, and they sometimes fix them. It's been good in that sense. Recently on the oneAPI consumer stack, it's actually been pretty decent in the last like 8 months. Typically, integrated graphics cards just work pretty much. And then through the SYCL side, you always, by the API, you're guaranteed to have the CPU device. So you always have something to run on at the very least. I know SpearV there were some bugs that Carol was dealing with. And it looks like one of them might have gotten fixed recently. Related to Carol's work, I remember a ways back, he was talking about Mesa being able to, and having a system so that Rustical would be able to consume a SpearV as a runtime. And I was wondering if that's the plan longer term from like a SYCL vendor standpoint or compute standpoint. Would binaries purely shipping their compute SpearV, I think it's on the, I forget which control flow version it is, but would that be something that Mesa would be looking to accept as, oh, we want to run on everything, we'll handle running everywhere, and then binaries in general just target outputting SpearV? And then we'll deal with it from there. Okay.
Yeah, I think that's where, I think that's the best possible future with the technology we currently have, is that you would have, you would be able to build a binary from SYCL or Rust or whatever it was. You would have an ELF file. The ELF file would have CPU code and GPU code in it. The GPU code would be SpearV. and you would then have the backend, when you execute it, build it and cache it or whatever you need to do at runtime. There may be scope again for, so this is one thing Vulkan, I said, doesn't do, but CL has a bit more about that, is that you could have like we have libclc, which is a bunch of runtime code that's to be optimized in the backend. Currently, when we use libclc in our stack, we build all of that into the SPIR-V. We don't use that in the back. We convert libclc to SPIR-V and then just join it to the other SPIR-V we get from the user. We don't have a targeted libclc. We don't have like specific libclc code for Intel and for AMD. There is code in there for that, but not in the way Rustical works. And how we could move towards bringing in vendor optimized libraries, like again the DNN stuff and that, that all those libraries that exist in outside of just, hey, I can do division faster, or I can do this small, FMA a bit different. Those with optimized kernels and adding libraries of optimized kernels, but trying to make those libraries of optimized kernels have a standard, like having a standard place for them to live. It would be, because you go into the area now and you're like, oh well, you got all DNN libraries, you got BLAS, every vendor's got its own fork of all of these things. I got to ship, and people don't know which ones they need. Again, from a vendor just giving you a stack, it's not so bad. When you're trying to distro this, it's like, how many of these different forks of things am I trying to get here? It'd be nice if there was like a vendor repository of, here's some source code and here's some binaries of optimized kernels for these GPUs and all the AMD ones, all the Intel ones, and they're all there. And we use, or it could be in Mesa, it could be out of Mesa. I don't, but that having that sort of, again, non-vendor community focused area for these things to land, and then non-vendor people can push optimized kernels as well. Like you don't have to wait for AMD to optimize these things for your hardware. If you want to sit down and optimize it for your hardware, you do it, you contribute it, it's there. The next release picks it up. It's again, it's trying to build that community and opening it to people that are not part of the company or not part of the vendors. Like in the end, it will be better for the vendors. It's just they need to be dragged to that point. Maybe except for NVIDIA. But the other vendors will be better. They're second movers. They need to figure out where their distinctions are. And I think that's one area they could make a big distinction.
Yeah, because I mentioned this in the chat a little bit, but I've been back and forth with some of the NVIDIA folks and some of the AWS folks. And it looks like there's already headers in place targeting release 540 for NVIDIA to be able to consume SPIR-V. So at that point, does that, and this is more directly like opinion and crystal ball stuff, but at that point, does SPIR-V become the default? How do you get compute to run everywhere? Does that become the default?
I think if we could get it to the ROCm does it, ROCm I think is kind of on the way to doing it as well. I don't think they've quite got there. If both ROCm and NVIDIA and Intel stack at least could consume the same SPIR-V, that would be a good thing, because that would give Rustical a good, I know what I'm going to get sort of target. There's still a bunch of work we need to do in Rustical backend compiler stuff, to consume all of that stuff. But at least you have a general target. Again, it would, in that you could make Rustical to GCC, and the vendors then would still have their own optimal things you can ship. But you could at least build distros with PyTorch that works out of the box and is useful out of the box. And then if somebody goes, oh, I need that extra 10, 20%, that again, HPC people are always building everything from scratch. So like that's what you do. It's like, there's no real pushback from that area to go, oh, I need binaries, I need build things. It's like, no, we'll just rebuild everything. It gives us 5%. It's what we're going to do. And that's fine. That works for them. But the companies are very, because that's their market, the vendors are sort of stuck into that cycle of, we have to make the HPC people happy. And it's like, it's just not good for distributions. Again, if people want to see AI and machine learning, I want to be able to run Llama out of the box on whatever hardware I have and see if it works and play with it. And if it doesn't work, well, I get better hardware. But you shouldn't have to build specific bits of these things for every single card and have to install these huge stacks just to run a quick AI model that somebody's released.
Yeah. So kind of from there, one of the things I'm curious about is when you have under SYCL, when you have your host device and then you have your graphics device and then you end up with your accelerator device, which can be an FPGA, but can also potentially be something like a Habana device. Those devices, because they're glorified ASICs, right? That only take, we're doing FMAs of n by n matrices. Is that something that realistically can be supported by Spear V compute, right? And is that something that makes sense to have as an accelerator under a Mesa or some other subsystem, especially now that accelerators are being pulled out of DRM and as their own thing in the kernel, right?
I think the work that Tomo is doing on the inference accelerators is very valuable in that space. There's no good API at the moment for inference, really. There's been, I think that I'm not going to say because I'm not sure if it's public, other thing, but his work he's looked at. So I think there's I'm trying to remember the name, but TensorFlow Lite has a delegation layer, and that's what you use to delegate certain operations off to the inference accelerators. And I think PyTorch probably has something similar. And his work in that area is to try and use those delegations, but they're not. Those delegation layers are inside the stack. There's no real standard API, and he's trying to bring that into Mesa so that he could add the Mesa. Mesa would run the and then provide a delegation API. Then we would see whether we could make a delegation API that PyTorch, TensorFlow, anyone else could use. But that would be where we want to go with those sort of devices that are limited. I see Baz has a hand up.
Yeah. So one of the problems, of course, from the distributions is that like you have to recompile your PyTorch for every new API, and like the delegates for like TensorFlow Lite are a solution to that, even if you have different APIs. But I think there are some developments on there, like API-wise, also on the bigger frameworks. Like Google has the same problem for the GPUs, of course, like hey, vendor API. And of course, as TensorFlow producer, they have been dealing with that. So I think with TensorFlow and XLA, like their machine learning compiler, like they've been working on plugin architecture, and I've seen attempts to actually get it working on PyTorch as well. So that might raise here and not give us like the ubiquitous compute. But if we're saying like, hey, there's no common API that makes the matrix multiplications fast, just pure compute, like, hey, that might be the other way this is going to happen.
Yeah, PyTorch has a plugin system. I know Intel are using it for the accelerator, not just the compute bit, but the actual neural network accelerator cores. And I think, that plugin system, again, getting that into a standard API would be probably some value, I think. Whether we do it in like a Vulkan API, compute it, OpenCL extensions, or, it's one of those problems. If you put it into OpenCL, it's like you would want it, the API would only want to be a very small subset of OpenCL. You couldn't accept everything and then try to make it run on that device. It would be like, no, you just program it like OpenCL, but it only accepts these operations, and the delegate deals with that. So it's getting that, finding an abstraction there is going to be tricky and fun, I suppose. But I think we definitely need something like that to bring those accelerator devices in.
I guess I had more of a comment since, I'm sort of the community interface to oneAPI, right? So a lot of what you've said resonates with me in terms of what is the community's perception of oneAPI and so forth. And building that trust is something I've been really focused on. One of the things that I like to see and I'm trying to drive is community builds, right? Like, what is the fully open source, all of it put together in a single build that people can easily consume? Because from there you can build packaging as you're talking about, maybe Fedora. But once you do that, because most of the packaging has been vendor based, and I would like to see sourcing for packaging come from the open source builds that we have rather than going through the other. And so that's kind of sort of the things I like doing that.
That's and I sort of like the question I generate when I've gone into meetings over the years with vendors about their stacks. It's like the first question you do when you walk into AMD about ROCm is like, so if we port this to Intel's hardware, will you maintain it upstream? Will you allow it up into your product? And I say for Intel, it's like, the question you ask is like, if I port oneAPI to AMD and NVIDIA, are you going to, is that an acceptable thing to go upstream into your project, the project area, and be something we can consume later, or do we have to maintain that forever on the side? And if the answer isn't yes, we'll take it, then we can never use that project as a basis for a heterogeneous commoditized project, because you need to have that. Yes, we're willing to deal with our competitors, and Linux does it great, Mesa is doing it great, but yeah, we are in a bit of a in my mind, we're probably where Mesa was 20 years ago in the compute stack, 15, 20 years ago, like in that it was just a while where everyone had, we had one really good NVIDIA OpenGL driver and a lot of crap OpenGL drivers from everyone else, and it's like we've changed that a lot. I'm doing the same with compute, getting it to that level. Again, GCC probably wasn't the best compiler in the world when we started with it 20, 25 years ago, but again, it's a baseline and it's there, and that's all that really when eventually all that matters. It's not all that matters in the HPC, and it's not all that matters in the data center, but it's all that matters when you just want to run something on your laptop or on your desktop, and I sort of see it as we live in Linux kind of lives in an enterprise focused world where the desktop is more of a whatever the leftovers will flow down into the desktop, and it's like, that's the reality of where we live. It's just Red Hat's an enterprise company, NVIDIA's Intel are all trying to sell data centers and HPC stuff. So
I think the GCC thing is that it just made programming available for everybody. Right?
Yes.
Back when I was a kid, you paid $200 for a compiler.
Yeah.
I mean, for a C compiler, and suddenly you get it for free, and that's where we're able to build an entire ecosystem of software, because we made it available thanks to being able to have a compiler with the source available and improve it. Right? It started off one way, and then it evolved to be a really great.
Actually, another project I'll just mention. I don't know how it's going to go. As I've looked into. There's a company called Modular that's doing a thing called Mojo. That's a Python compatible language that will be more AI compatible. It's going to be a runtime compiled and stuff. I haven't had a chance to reach out to him. It's run by Chris Latner, who's done a lot of LLVM work in the past, and he's done some RISC-V stuff. And I think they haven't released yet, but their plan is a runtime Python compatible language, but that's actually not interpreted, compiled. But they're want to be able to target AI accelerators. That's their big thing, is to target all that area.
Is that Triton?
No, it's Modular and Mojo.
Yeah, I thought Triton also had a Python like.
Yeah, so they're there. I've only heard him talking about it, and I think he's releasing. But again, I want to reach out to him and talk to him about runtime at some point. I just haven't had a chance to schedule. Again, that's the sort of development I'd like to see, being able to, based on the cycle working, that how do we use that infrastructure we've built. Yeah, what Carol's saying is it's true. CUDA is just there. It works for everyone. Everyone gets to play with it. But developers want to be able to do these things on their laptop and screw around and not have to go into Amazon and or even if they do, they want to be. Have you tried to get an NVIDIA GPU in AWS? Good luck. It's like you definitely won't hold on to it for long if you're not using it. So cool. Are you going to publish this to YouTube afterwards? Is that
what was it again?
Are you going to publish this to YouTube?
Yes. Yeah. I'll publish it to YouTube. Yeah. So I'll get those recorded. And I think this is like a talk for a lot of vendors to be able to disseminate and understand. I think I really enjoyed this talk simply because you're providing a community perspective and expectations that sometimes hard to get. Especially in this space, because it's such a niche space, right? It's not everybody knows all Spear V and and all this, and so that I think be able to bring that perspective and be able to disseminate that amongst all vendors is something very valuable. So, does anybody have any more questions? I think we have time for one more.
Well, so thank you for the talk, and I think that there's a lot of people inside the companies think like you, but well, it's difficult to percolate all these ideas across organization. But definitely, I will use your talk to send inside some ideas inside AMD, for example. So that's thank you for this talk.
Okay. Sorry, I didn't get enough FPGA content in for you and Tim.
Yeah, the FPGA compute problem is a bit of a sore spot there. You had Tricycle for a while supported as like a Sickle FPGA stack for Xilinx, and then that all died when the acquisition happened.
Ronan's still working on it.
Is he still going? Is that actually
still going on Tricycle?
Yeah, I would say it's mostly in maintenance mode. I agree that it's not super fashionable nowadays. But
I still get CC'd on all the commits. So
but it's still Sickle is still a product for our competitors. So unfortunately for us.
Yeah, completely unrelated question here. Dave, just wondering if you ever hired any of those Russian pilots that were sending you CVs from 25 years ago?
I think they've been trying to hire me. No, not yet.
Good talk. Just when I saw the name pop up, I was like, Jesus, I haven't spoken to Dave in 20 odd years.
It's been a long while.
Certainly has.
Cool. I think we've reached the hour, have we, Sri?
It looks like we reached the end. I'd like to thank everyone who actually, even though it's 1 or 2 a.m. in their time zones, it still took an interest to come. And of course, Dave, thank you so much for this talk and accepting our invitation to come and talk here. And I will have this video is recorded, so I will save it, and then y'all can distribute it once I get it on YouTube. So thanks everyone for coming, and we'll see you next time.
Thanks, Ray, for hosting.
Yep.